Still working in section 2.3, the precise definition of a limit. So we're going to do something very similar to what we did in the last example, except now we're going to actually be given a precise number for epsilon. Otherwise, it's pretty much the same thing, okay? So if we're given a precise number for epsilon, we want to be able to find the precise number for delta that makes this statement true, which is our definition of the limit, right? So the way we have to do that is in two steps. One, we need to go ahead and solve the inequality. Again, it's like work backwards. Take your f of x minus L, the absolute value of that, less than epsilon, to find some open interval containing x naught on which the inequality holds for all x. It isn't x naught. But then we'll go ahead and find a value of delta that gives us an interval that's equal on both sides of x naught. That's the best way to look at it. Okay, so let's look at this function. Example 12. For the limit as x approaches 5 of the square root of x minus 1, again, this is simple. We could just plug in 5 and we can see that that's 2, right? We plug in 5, we get the square root of 4, which is 2. Not plus or minus 2, because we're talking about the function, the square root function. So it can't be plus or minus 2, only 2. We want to find a delta greater than 0 that works for epsilon equal to 1. Now you're told epsilon is 1, not just any epsilon. Epsilon is specifically equal to 1. So what's the delta that makes this limit work? Well, again, I need to find the delta, so the distance between x and 5, x naught, x is approaching 5, so the distance between x and x naught is less than that delta, tells us that the distance between the function and its limit is less than 1 because we're forcing epsilon to be 1. So just like we did in our previous example, work backwards from this guy. Backwards from the absolute value of f of x minus L is less than epsilon. Work backwards from that to find some open interval around x that contains x equals 5. Okay, so you work backwards. So know when I have an absolute value inequality, what I do is I remove the absolute value by saying it has to be greater than minus 1 but less than 1. Right? I bring this 1 over to this side, make it minus 1, and I have these two inequalities essentially. So now I'm going to add 2 everywhere. Add 2 to 1, I get 3. Add 2 to negative 1, I get 1. So that means the square root of x minus 1 is between 1 and 3. Then I square everything. So when I square x minus 1, when I square the square root of x minus 1, I get x minus 1. When I square 3, I get 9. And when I square 1, I still have 1. Then I add 1 everywhere. So x then is between 2 and 10. So that tells us that the absolute value of the square root of x minus 1 minus 2 is less than 1. Holds for all x in that interval between 2 and 10, because we started with this and we worked backwards. So it certainly holds for x not equal to 5 in that interval. As long as x isn't equal to 5, it holds. Okay? So what's the delta that works? Well, remember I want to be equal distance from 5 on both sides. So 5 is closer to 2 than it is to 10. So we're going to take the distance from 2 to 5 and go on the other side of 5. That would be from 5 to 8. So the interval I really want to think about is from 2 to 8 instead of from 2 to 10, because that surrounds 5 equally on both sides, which tells me that delta is 3. I can only be 3 away from 5, right? 5 is only 3 away from 2. It's 5 away from 10, so I don't want to take delta to be 5. I have to take it to be 3, because x is approaching x naught. X is 5. So 5 is in the middle. That means I need to be the smallest distance, which is 3 from 2, not 5 from 10. So delta is 3, implies that the absolute value of the square root of x minus 1 minus 2, the distance between the function and its limit is less than 1.